Okay, so good evening, everyone. Welcome to the sixth live problem solving session for this course, Aqueous Corrosion and Control. Um, so the next assignment, 5, is for both week 6 and 5, 5th and 6th week. So it's due tomorrow, so I cannot discuss it today. Uh, but if you have any, like, if you solved it and getting some incorrect answer or something like that, yeah, you can. If the options are not matching or something like that, then you can just maybe type in the comment chat box and you can try to solve it at the end. Or yeah. So for now, I we had a some practice problems. I was hoping to cover those this week. So from now on, I think for every 2 weeks there's a single assignment. So I'll discuss those assignments for the weeks. Okay. So, this next Tuesday. And, yeah. So I can start with the first problem. I think people will be busy at the match today. So I don't know how many will join. And they can watch it on YouTube later. So the first question is, what is the equilibrium potential for Fe equals to half cell at 25 degrees centigrade when the concentration of Fe in the solution is this and this. If both cells are connected, which of the two will be anodic? Okay. Uh, so we have reaction P two electron. Like the reduction. So two electron P and reduction potential. You get the rest equation becomes E is equals to E naught 2 log of V is to Y. Oh, oh. So for the first case, Fe is to and concentration is 10 to the power minus 6. Okay, E naught. E naught again is missing here in the data. E naught was minus 0.44 volts. I think in the next question there's some, it's not a fourth question, there's some, let's see, what are the again? Is equals to E naught 0. No, by the way, this is from the example problems. 2 log of 10 to the power minus 6, 0.4 plus 0.059 into 10 to the power minus 6. We get minus 0.44 into 0.3 minus 1 here. And yes, we get minus 0.44 minus 77, 0.676 volts for this is for 10 to the power minus 6. For the second case, where again concentration is 10 to the power minus 4, E equals to E naught plus 0.0 log of 10 to the power minus 4. Just 4 minus 0. 9 2 4 minus 855. Yeah. So now for E cell has to be positive, so E cell is described as E cathodic mass, E anodic. This value has to be positive, so based on this, we will decide which of the two solutions will act as cathode and which will be anode. So we have two potentials. E cell given we are given plus minus 0.617 volts, and E2 was minus 0.558 volt. So for the E cell to be positive, and this has to be a cathodic half, and this will be another half. So cell is minus 0.558 plus 0.59 volt. So yeah, 10 to the power minus 4 mole solution. Solution acts as your cathode. And yeah, 10 to the power minus 6 solution. Cathode. I will like to see the other way, like this has less amount of Fe plus 2 ions, and for equilibrium to happen, both it needs to have equal concentration, equal voltage, and the concentration would become kind of equal. So here more Fe would get oxidized, and more Fe plus 2. So, I think they'll reach a value in between where the concentration becomes equal. Mm, by the way, I did mail Professor Raja today regarding that question from assignment 3. Let's see, he hasn't replied yet. So I'll let you know. Okay, the second question in the problem example problem was an iron rod injected in HCl at pH 4. What should be the equilibrium concentration of Fe plus 2 for so that the corrosion of the rod stops at 25 degrees Celsius? We are given the partial pressure of S2, 1 atm, and the standard reduction of potential iron. Okay, so when you apply the last equation, and turn it into unstable. Hopefully you guys are able to hear me. Uh, Dipped in HCl, so we have reaction happening. X plus X plus, we can get P plus 2 plus 3. There are two halves of the reaction. X equals to P plus 2 plus 2 electron, and 2H plus 2 electron can be H2. Using the last equation, we get in the standard reduction potential. The reduction potential for Fe is minus 0.44, 0.059 divided by 2 log of Fe and concentration. This is what I have to calculate. The Fe and concentration. In the second half of the reaction, the reduction potential for hydrogen 0 plus 0.059 divided by 2 log of the concentration divided by pH2. This we are given as 0.99 divided by 2 log of H plus ion concentration is 10 to the power minus 4. Log of 10 to the power minus 4 divided by 1. So we get minus 0.18. Oh yeah, that's square. And so that becomes minus 0.22. Right. Six. 1236 volts. And yeah, sure. I'll upload it right after the session. Mm, mm. Yes, and to stop the corrosion, stop corrosion, your E cell should be 0. Cell is equal to 0, so your E cathodic should be equal to E anodic. So, your E cathodic is 0.236 volts, is to 0.044 plus 0.03, 0.9 divided by 2 log of, sorry, not H plus, log of Fe plus 2 ion concentration. Okay, and if you just take it to the other side, 0.44 minus 0.236 is equals to 0.59 divided by 2 log of 2. Subtract these two. You get 0.204 into 2 divided by 0.059 equals to a log of Fe to ion concentration, which becomes 6.95. That's the log of Fe plus 2 ion concentration. Fe plus 2 ion concentration becomes e to the power 6.915, like it as 10 to the power 0.615, 695, 915 into 10 to the power 6. And this value I'm getting a value of 8.24 into 10 to the power 6 moles per liter. Slightly different from the solution. Maybe it took 0.03 instead of 0.05. Mm, yes, yeah, that's what we're getting. Nothing in even in this final examination will be objective subjective type. Not be an issue. Okay, so third question is what voltage needed to be applied on platinum and zinc? Halogen needs to be generated. A plate of this and the electrolyte used for the catalysis is water at H2 exchange current density for H2 H plus reduction is given on different metals, platinum, nickel, iron, zinc as its values, and minus 3, minus 4, minus 6, and minus 9, respectively. The Tefel slope for the hydrogen reduction reaction is given. So let's see. So let's first calculate the current density we need. So we are asked to generate 10 to the minus 6 moles per second per centimeter square. So reaction is H plus 2 electron. Yes, H2. So the current required for 1 mole of to convert 1 mole of material into like charge transfer for 1 mole of material, 1 mole of hydrogen reduction would be um, charge is equals to 96500 into 2. This is for 1 mole, so so if you do this per second, so this is your current. This is for 1 mole, so for 10 to the power minus 6 mole, the current would become I is equals to F into 2 into the concentration, the molarity rate of generation. So it becomes 96500 into 2 into 10 to the power minus 6. This is your current density, 5 per centimeter square, amps per centimeter square. Okay. This becomes 9.65 into 2 into 10 to the power minus 2. 0.0 16, 0.193 amps per centimeter square. So this is your IE cathodic. Now for the cathodic reaction, suppose was you can write the TEFL equation for cathodic minus beta C log of I cathodic divided by I naught. This is a TEFL equation, and that equation for platinum. We are given the exchange current density for the reduction is 10 to the power minus 3 amps per centimeter square. The overpotential is given 0.12 volts. Right. And so the the overpotential becomes minus 0.12 log of our required current density, which is cathodic current density IC, which was IC is equals to 0.193 amps per centimeter square. IC is 0.93 divided by naught minus 4. This value is 0.12 log of 3 to 10 to the power 4. So this becomes
Excuse me, it is 10 power minus 3, I think.
minus 3. Okay. Thank you. Yes, for platinum was minus 0.12 log of 193. I should translate it. Minus 193. Minus 0.12 into 2.8828, sorry, 0.285 to 0.2. So you get minus 0.274 volts. Okay. Similarly for nickel, here the exchange current density is 10 to the power minus 4. C is 0.12 log of 0.193 Right by 10 to the power minus 4. 3030. No loss. Yes, 0.12 into 3.285 and get for potential of 0.394 sorry, volts. Repeating the same thing for iron. Iron uh, current density environment 6. Right. So it has ridiculous minus 0.12 into log of 0.13 divided by 6. Zero, zero, two. This minus 0.12 into 10. 5.285 minus 0.634 volts. And finally, for zinc, uh, section exchange current density is 10 to the power minus 9. Beta C is 0.12 log of 0.193 divided by 10 to the power minus 9 to 193 into 10 to the power 6. 6. And this you get 5 to minus 0.994 volts. Okay, this is your over potential. Now the equilibrium potential, we need to calculate using the math equation. So EH plus H is to be minus 0.059 into log of plus and concentration. It's an concentration. Water of pH 2. pH is 2, so it's an concentration is 10 to the power minus 2. Motivated 0.059 into 2 minus 118. 0.1 volt. This is your equilibrium potential. Now your over potential would be different between the applied potential minus your equilibrium potential. We calculated our applied potential here. So if you just imagine the events diagram, this is for platinum. H to H on PT and minus 4. It should be sort of actually. Towards this over here. The slopes are even all the same. It's just a this is a 10 to the power minus 9, 10 to the power minus 6. Where is it? No, minus 3. This is H plus H on platinum. So, on nickel. This is reduction potential on iron, P, and primary. So we don't know where the oxidation off is happening, but we know the equilibrium. So this should be, I would say, minus 0.118. The equilibrium potential is given at this, it is the pH value. And now you're applying some potential, so to get the this is the rate of cathodic current we want. Which is around 10 to the power minus 1, right? Yeah, 2 into 10 to the power minus 1, so somewhere out here maybe. So again, the x-axis maybe shifted into somewhere out here. So these are the potentials we have to calculate. We have four potentials we have calculated. This value, this value, this value, and the difference between them is your core potential, theta. So this is the equilibrium potential, and this is the E applied. We get that value of current, cathodic current. Okay. So for platinum, your eta was 0.274 volts, and eta is defined as P applied minus equilibrium. And E applied is what we have to calculate. So E applied equals to Eta plus E equilibrium. So in case of platinum, energy applied will become 0.274 plus minus 0.18 and minus 0.392 millivolt. Similarly for other metals, for nickel, we applied minus 0.394 4 minus 0.118. This becomes minus 512 volt. And for iron, we applied minus 0.4 and 0.634 minus 0.18 and minus 5 and 0.5752 volts. And finally for zinc, we applied 0.994 minus 0.8 get minus 1.112 volts. So this is like how much biasing you need to give to these metals to generate hydrogen. So if you know anything about like hydrogen evolution reaction HCR, where metal is dipped in some solution and you run it against a counter electrode, it's usually like either carbon or so this is assume this is a platinum, and this would be a solution with pH 2. And you have your counter electrode, which would be maybe platinum or carbon, graphite, and you run apply some potential, say over potential, to drive the hydrogen emission reaction. So here, the lowest over potential we see is for mm, platinum. So the platinum is the most effective, at least for HER reaction. I can say something like this. Okay. Mm, mm, mm. Determine the corrosion potential, corrosion current density for zinc in 1 molar, one normal HCl. It's just 1 molar HCl. Assume that all nickel surface acts as a cathode and the Teflon slopes are 0.1, and the exchange current density for zinc and the hydrogen in zinc is this values. Things from the nature. This is a standard reduction potential for zinc. Zinc is minus 0.44. And yeah, if you get this question asked in the exam, you can assume any concentration and solve it for like that. Uh, for zinc and concentration, since you're not given either, I don't think you'll have an option to ask the examiner, but yeah, just assume some value and solve it. And uh, anyways, we have to like we usually go and check the copies one by one first. We'll solve, check the value and calculate the answer regarding up to that value, taking that value. So for hydrogen, the equilibrium reduction potential becomes is equals to 0 minus 9 divided by 2 h log of h and concentration. And yeah, partial pressure by 2, whereas general is 1 atm is 2, 0 point. H and concentration here is 10 to the power minus 1, this is 1, so this value 0 plus 0.059 log of 1 over 1, 0. Reduction potential is 0. Reduction potential for zinc. So E zinc plus 2 plus equals to minus 0.44 plus 0.059 divided by 2 log of zinc and concentration. Right. 2 into log of 10 to the power minus 6. Minus 3 times 0.059. The weight is 0.44. Yeah, minus 0.617. Okay. Okay, I did a mistake. So notice this is for iron. For zinc, it's different. Standard reduction potential for zinc is like 0.763. Yeah, and change here 0.763 and 0.763. It would be a good idea to remember that, like for zinc and iron at least. Yeah, since I've solved so many questions in the assignment, so it would be handy to remember these two values. 0.44 for iron and 0.76 for zinc. Okay. Mm, you just have to write the Japanese questions. for the cathodic and anodic part. Anodic, let's go. E corrosion minus zinc plus 2 zinc. E and delta cathodic would be E or minus E H. Give me a second. Sorry for that. Yes, so cathodic and anodic mode potential. Writing the Tafel equation, beta log of I core I naught, and for cathodic minus beta log of I core I naught. So substituting this two, you get E core minus the cathodic part minus 0.1 log of I core divided by current density, just 10 to the power minus 4. And E core is general reduction potential for zinc. 1 log of I core 8 to the power. It's 1. I have two equations. This value is 0. This value will get minus 0.97794. I have two equations to variable. If you subtract these two, subtract the 1 from 2, you'll get 0.94 equals to log of I core minus 0.1 log of small 1 plus 0.1 log of I core square into 10 to the power minus 5. 0.94. If you take this to the other side, you get minus 9.4 log of I bar square plus log of 10 to the power 5 is 5. Mm, Okay, so this I made a mistake here. So this is minus of minus 0.94. Right. So this becomes minus. Oh, this value changes. So this becomes plus, yeah, log of I core square is equals to 4.4. So log of I core is 2.2. I core standard power 2.2, which is 158.5. So I core 158.5 grams per centimeter square. I think. This is meter square. Okay. Amps per meter square. This was stand upon. Right. So to get E core, you get E core is equals to, if you just copy this equation, E core is equals to minus 0.1 log of 58.4 divided by 10 to the power 4. You get minus 0.1 into 6.199 minus 0.621. I think exact same sort of question has been solved in the assignment too. Hopefully they should have given questions for at least for the practice assignment. So there's a different PA who handles the assignments and making the assignment again. I think she answers and also replies on the forum and the questions. Yeah. I think she would be a better person to answer the assignment questions. Yeah, we can try it. We try to solve it here. Okay. Can I explain it? I'll be back in 2 minutes. Okay. Okay, for assignment, maybe. Did you try to solve the assignment? If you have any question, like queries, any confusing answers, you can ask me now.
Please solve previous assignment problems. I have a lot of doubts on that.
For assignment
One
4,
assignment 1 4 I have. It is I know from previous problem sessions last week assignment problems, but before that 1 2 3
oh,
assignment
1 and
problems.
2.
Nice.
I have YouTube videos on those. If you have any particular question, you can ask. Uh,
But only I want to problems. I didn't
uh,
understand that previous assignment problems. 1 2 3.
1, 2, 3. Okay, I can go through particular question if you want. Do you have any questions in mind, like uh, from those assignment
I didn't understand that problems itself. That's why I'm asking.
problem itself
Uh,
for
can you
all the
explain
problems in assignments?
assignment
First,
problems? Assignment
which
problems.
one? Yeah.
1 2 3. Can you explain in next session at least next week session?
Okay.
Hmm.
Okay. You mean the fifth assignment, question 1 to 3, right?
Yes, sir.
Okay.
Sir.
I thought you were asking me for an assignment, previous assignments.
Yes.
I can like we can discuss a bit like what would be the approach and all. I can try to explain it to you. Just open it. The first question we have steel is immersed in sulfuric acid and exhibits corrosion potential. This and we are adding two inhibitors which where the corrosion rate decreases. In one of them, the corrosion potential shift to this value -8. Another it shifts to -0.65. So like depending on which side it shifts, you can say if it's a cathodic or anodic inhibitor. Like it was covered in the lecture. Like just to give you an idea,
Negative, I think cathode.
if it is becoming more negative, it becomes cathodic, and if it becomes less negative, positive, it becomes anodic. So, and I think it was shown in the one of the video lectures. The professor showed like, which cathodic or anodic inhibitor which side the potential shifts. Primary reason for conversion coating. This was discussed in the lecture, but it can be a bit confusing. So, even in the last session, one of the students was asking, he thinks like two of these are correct, but he also thinks it provides adhesion strength for electrodisposition as well. In some cases, it does. I don't have a particular example, but maybe if you're preparing the surface for better electrodeposition, you can use the conversion coating. But I don't know if it's called exactly that thing. So yeah, just to know the C is not the correct answer. Not at least the answer they've given us. So yeah, as these assignments, a lot of questions are ambiguous. There are some language issues and all. Yeah. phosphate conversion coating. I think this was discussed in the.
Phosphate, I think more.
So
Last one,
manganese phosphate. Last question here.
manganese more, more resistance. Then last one is iron. So in between zinc, phosphate.
Yeah, you're correct. Platinum, allowing platinum with which of the following metal will lower corrosion rate? Again, this was shown in the lecture this week, I think. This was related to what was it? Just open the slides. Yes, passivating steel for dehydrated acids. In this slide. I think this was covered this week. So if you have iron, stainless steel, and your I not changes. So for if you have stainless steel, you add some little bit of you attach it with platinum. Your the current density increases and goes beyond the critical current density and reaches the passivation region. So it passivates your sample. Commonly used in titanium. Yeah. Mm, Again, sixth one is metal. Leak matches. Getting matches. Next one, rod is immersed in HCl solution. You're given a Fe iron concentration. Corrosion rate you're given. Solution has hydrogen gas pressure. Partial pressure is given. What would be its overformation to enable such corrosion rate? So this. So you have to calculate the over voltage, right? So from the rate of corrosion, you can
Answer
calculate
is C, I think.
C. Yeah, your answer is correct. So the solution I have. So you have solved this one as well. And finally, relief production is possible only if
This is also C.
yeah, I think this is uh, directly from the lecture. Yeah, C is correct. Yeah, I think you have solved the most of this I need.
In next week, I need information on the previous 1 to 3 problems,
1 to
answers.
3. Okay,
1 to
yeah,
3.
we can discuss them more detail. Like,
Right, right. Thank you.
yeah, okay. Uh, yeah, I think we can close the session here.
Right, right, right.
Okay. Yeah,
Thank you very much.
thank you for attending. Enjoy the match if you like watching cricket.
Right.
India wins or not.
Mm,
Chala, see you. Bye.
Bye.